Welcome to Chapter 2 of our exploration into the fascinating world of machine intelligence, titled The Lovelace Test, Beyond Turing. In this chapter, we will venture beyond the foundational concepts established by Alan Turing and delve into the visionary ideas of Ada Lovelace. Her pioneering work not only laid the groundwork for modern computing, but also challenged us to reconsider the potentials and limitations of artificial intelligence. We'll examine how her insights have influenced the evolution of AI, particularly in assessing creativity and originality in machines. This journey will take us through philosophical debates, contemporary evaluations of AI, and the ethical considerations that arise as we push the boundaries of what machines can achieve. In this chapter, we will embark on a comprehensive journey that begins with Ada Lovelace's profound vision and contributions to computing. We'll explore her unique perspective on machines and their capabilities, setting the stage for our discussion on creativity and the Lovelace test. The Lovelace test serves as an alternative to the Turing test, focusing on a machine's ability to generate original ideas rather than merely imitate human behavior. We'll then delve into the Cartesian test for automatism, drawing from René Descartes' philosophical views on consciousness and the nature of machines. This will lead us to examine the interplay between minds, machines, and Turing's perspectives. We will assess contemporary AI through the lens of the Lovelace test, evaluating how modern advancements measure up to its criteria. The role of human-AI collaboration will be a key theme, highlighting how synergy between humans and machines can enhance creativity. Finally, we'll address the ethical considerations inherent in the Lovelace test, culminating in a summary that ties together the insights gained from this exploration. Let's begin by delving into the life of Ada Lovelace, a remarkable figure whose legacy continues to influence the field of computing and artificial intelligence. Born Augusta Ada Byron on December 10, 1815, she was the only legitimate child of the famed poet Lord Byron and Isabella Milbanke. Following her parents' separation shortly after her birth, Ada was raised by her mother, who was determined to distance her from her father's tumultuous and artistic reputation. To this end, Ada's mother placed a strong emphasis on science and mathematics in her upbringing, an unconventional focus for a woman in 19th century England. Ada exhibited an exceptional aptitude for mathematics and analytical thinking from a young age. She was tutored by some of the most prominent mathematicians of her time, including Mary Somerville, a distinguished scientist and one of the first women to be admitted into the Royal Astronomical Society. Under Somerville's mentorship, Ada's talents flourished, earning her the nickname Enchantress of Numbers among her contemporaries. At the age of 17, Ada's life took a pivotal turn when she met Charles Babbage, a mathematician and inventor working on the groundbreaking Analytical Engine, a mechanical general-purpose computer that was revolutionary for its time. Ada was captivated by Babbage's ideas and became deeply involved in exploring computational concepts with him. Their collaborative relationship was instrumental in shaping Ada's visionary insights into the capabilities of machines, extending far beyond mere calculation. Ada Lovelace's most significant contributions to computing emerged through her translation of an article by the Italian engineer Luigi Menabrea, who had written about Charles Babbage's Analytical Engine. While translating the paper from French to English, Ada didn't simply convert the text. She augmented it extensively with her own notes and commentary, ultimately tripling the length of the original document. In these comprehensive notes, Ada demonstrated a profound understanding of the analytical engine's potential. She described in detail how the machine could be programmed to compute Bernoulli numbers, a complex sequence in mathematics, effectively outlining the world's first computer algorithm. This accomplishment has earned her recognition as the world's first computer programmer. But Ada's vision went even further. She foresaw that the analytical engine could manipulate symbols in accordance with rules and that this capability extended beyond numerical calculations. She suggested that, given appropriate algorithms, the machine could be used to create music, art, and literature. This was a revolutionary idea at the time, introducing the concept of artificial creativity and computational universality, the notion that a computing machine could perform any mathematical or logical operation. One of the most profound elements of Ada's work is encapsulated in what is known as no G in her expanded translation of Menabrea's paper. In this section, she speculated that machines like the Analytical Engine could one day compose elaborate and scientifically profound pieces of music or art if they were provided with the right algorithms and data. This foresight effectively anticipated the modern field of computational creativity. Ada emphasized that while machines could follow instructions to manipulate symbols, they could not originate ideas themselves. She famously stated that the Analytical Engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. This insight highlighted a fundamental limitation of machines. They lack the ability to generate original thoughts independent of human input. Ada Lovelace's pioneering ideas have had a lasting influence on computer science and artificial intelligence. She laid the conceptual groundwork for thinking about machines as more than mere calculators. In recognition of her contributions, Ada Lovelace Day is celebrated annually to honor women in science, technology, engineering, and mathematics, STEM. Furthermore, the Ada programming language, developed by the U.S. Department of Defense, was named in her honor, cementing her legacy in the field. Building on Ada Lovelace's insights, the Lovelace test was proposed by philosopher and cognitive scientist Selma Bringsjord and his colleagues in 2001. The Lovelace test was designed to address the limitations of the Turing test by shifting the focus from imitation to creativity. The primary purpose of the Lovelace test is to determine whether a machine can originate ideas or artifacts independently of human programming. For a machine to pass this test, it must create something that is genuinely novel and valuable, and its creation process must not be fully explainable by its programmers. This means that the output should not be the inevitable result of the machine's programming or a predefined set of rules. Instead, the creation should demonstrate autonomous creativity and unpredictability, indicating that the machine has operated beyond the explicit instructions given by its human developers. While the Turing test has been foundational in evaluating artificial intelligence, it primarily assesses a machine's ability to imitate human conversational behavior convincingly enough to fool a human interrogator. However, this focus on imitation presents significant shortcomings when considering the broader aspects of intelligence and creativity. One major limitation is that the Turing test does not address a machine's capacity for original thought or innovation. A machine could pass the Turing test by effectively mimicking human responses without ever demonstrating genuine understanding or producing novel ideas. Additionally, the Turing test emphasizes observable behavior over internal cognitive processes. This means a machine could rely on program tricks or pattern recognition to simulate understanding, without possessing any true consciousness or subjective experience. Furthermore, the Turing test fails to measure a machine's ability to contribute meaningful, new insights or creations to a field. It does not account for the rich complexity of human creativity, which involves not just responding appropriately in conversation but also generating original concepts and works. These limitations highlight the need for alternative measures, such as the Lovelace test, which focus on evaluating a machine's creative capabilities. The Lovelace test introduces specific criteria to rigorously evaluate a machine's creativity. First and foremost, the machine must produce an output that is genuinely original, meaning it cannot be directly traced back to its programming or the data inputs provided by humans. The creation should represent something new within its domain, not merely a recombination of existing components. Secondly, there must be unpredictability in how the machine arrived at its output. The creators or programmers should be unable to fully explain or predict the process that led to the creation. This unpredictability indicates an autonomous creative process that goes beyond mere execution of programmed instructions. The third element involves evaluation by experts in the relevant field. The output should be assessed for its novelty, value, and creativity, considering both the process by which it was generated and the final product. This ensures the creation holds significance and is not a trivial or random result. Lastly, the output must have non-trivial value or significance within its domain. It should contribute meaningfully to the field, whether it be in art, music, literature, or another area of creative endeavor. This dismisses outputs that lack substance or coherence, focusing on creations that have depth and relevance. To further understand the philosophical underpinnings of machine intelligence and creativity, we turn to René Descartes, a 17th-century philosopher and mathematician famous for his statement cogito, ergo sum, I think, therefore I am. Descartes explored the distinction between the mind and the body, delving into the nature of consciousness and what it means to be a thinking being. In his philosophical works, Descartes described animals and certain human functions as mechanistic, operating like automatons without conscious reasoning. He believed that while machines could replicate certain behaviors, they inherently lacked the capacity for rational thought and self-awareness that characterizes human intelligence. Descartes argued that the ability to use language in a flexible and contextual manner is a hallmark of rational thought. He posited that machines are incapable of such linguistic adaptability, as they lack consciousness and understanding. This perspective emphasizes that true intelligence requires more than just external behavior. It necessitates an internal subjective experience and the ability to comprehend and reason about the world. Building on his philosophical views, René Descartes proposed criteria, though not formalized as a test, for distinguishing true intelligence from mere automatism. According to what we can refer to as the Cartesian test for automatism, genuine intelligence requires consciousness and self-awareness. One criterion is the ability to use language appropriately across various contexts. An intelligent being should not only communicate but do so with understanding, adjusting language used to fit different situations and convey complex ideas. Another criterion is the capacity to exhibit adaptable and rational responses to new and unforeseen circumstances, demonstrating reasoning and problem-solving abilities that go beyond pre-programmed reactions. These criteria imply that machines, lacking consciousness and subjective experience, cannot genuinely think in the way humans do. For artificial intelligence, this presents a significant challenge, as it suggests that even highly advanced machines may be limited to simulating intelligence rather than possessing it intrinsically. The progression from the Turing Test to the Lovelace Test and consideration of Cartesian philosophy reflects an evolving understanding of machine intelligence. The Turing Test focuses on a machine's ability to imitate human conversational behavior, assessing whether it can produce responses indistinguishable from those of a human. In contrast, the Lovelace Test emphasizes creativity and the generation of original ideas, pushing the boundaries of what we expect from machines. It challenges AI to produce outputs that are not only novel but also generated through processes that cannot be entirely explained by their programming. Cartesian perspectives introduce an additional layer, arguing that true intelligence involves consciousness and subjective experience, qualities currently beyond the scope of artificial machines. This evolution highlights the need for comprehensive measures that consider behavior, creativity, and consciousness in assessing machine intelligence. It encourages interdisciplinary research that combines insights from philosophy, cognitive science, and AI development. In the contemporary landscape of artificial intelligence, we've seen remarkable advancements with the development of large language models, LLMs, such as GPT-3, GPT-4, and BERT. These models are capable of generating human-like text, composing music, creating art, and even writing code. They utilize deep learning algorithms to process and generate language, often producing outputs that are impressively coherent and contextually appropriate. When assessing these AI models using the Lovelace test, several questions arise. Do these models produce outputs that are genuinely novel and unpredictable? Or are they simply recombining existing patterns found within their extensive training datasets? While LLMs can generate content that appears creative, their outputs are fundamentally rooted in the data they have been trained on. They lack awareness or intentionality, operating without consciousness or a desire to create. This raises the challenge of determining whether the creativity exhibited by AI is genuine or merely an apparent byproduct of sophisticated data processing. Although AI-generated art and compositions have been showcased in galleries and performances, the debate continues over whether these creations meet the criteria of the Lovelace test. Applying the Lovelace test to current AI systems highlights several limitations. One key issue is explainability. Developers and programmers can often trace an AI's outputs back to specific algorithms, datasets, or training processes. This ability to explain the AI's creative process violates the unpredictability criterion of the Lovelace test, as the machine's output isn't originating beyond the scope of its programming. Another limitation is data dependence. AI outputs heavily rely on the training data provided to them. They generate responses based on patterns and information extracted from this data, lacking autonomous creative thought that is independent of prior inputs. Furthermore, AI systems do not possess understanding or intent. They lack consciousness and do not experience a desire or purpose in creating. Their actions are bound by programmed instructions and algorithmic constraints, which limits their potential for genuine originality. These factors suggest that while AI can mimic creativity, it does not yet achieve the standard set by the Lovelace test for originating truly novel ideas. Despite the limitations of AI when evaluated in isolation, there is significant potential in the synergy between human creativity and AI capabilities. AI can serve as a powerful tool to augment human creative processes, providing new ideas, suggestions, and variations that might not have been considered otherwise. In the realm of art, for example, artists are increasingly using AI to generate novel artworks. These collaborations can lead to innovative styles and forms that blend human vision with algorithmic exploration. Musicians are partnering with AI to compose music, exploring new harmonies and structures that push the boundaries of traditional composition. In scientific research, AI assists in drug discovery and materials science by generating hypotheses and identifying patterns that may elude human researchers due to the complexity or scale of data. Educational applications also benefit, with AI tools aiding in teaching creative writing and art by offering personalized feedback and stimulating creative thinking. This synergistic approach leverages the strengths of both humans and machines, expanding creative possibilities and fostering innovation across various fields. When assessing outputs generated through human-AI collaboration, it's important to consider whether the creations surpass what either could produce independently. Applying the Lovelace test in this context involves evaluating the novelty, value, and significance of the collaborative outputs. Transparency and explainability are crucial. Understanding the AI's role in the creative process ensures that its contributions are interpretable and accountable. This helps in assessing the extent of the AI's creative input and in maintaining ethical standards. Ethical implications also arise regarding authorship and ownership. Determining how to credit AI systems in creative works is complex, as it involves balancing recognition between developers, users, and the AI itself. Ensuring fair recognition and addressing legal considerations are essential to support ethical and responsible collaboration. Looking ahead, the potential for AI to become a creative collaborator opens exciting prospects. By exploring new forms of artistic expression and innovation, we can push the boundaries of creativity and expand our collective capabilities. The integration of AI into creative processes brings forth challenging questions about authorship and ownership. Legally, it's unclear who holds the copyright for AI-generated works, as current laws may not adequately address scenarios involving non-human creators. This uncertainty poses difficulties in attributing rights and responsibilities. Attribution is another complex issue. Deciding how to credit AI systems involves considering the contributions of developers who designed the AI, users who may have directed its use, and the AI's own role in generating the output. Balancing these factors requires careful deliberation. There are also economic impacts to consider. The potential displacement of creative professionals due to AI automation raises concerns about job security and the undervaluing of human creativity. This necessitates discussions on how to integrate AI while supporting the livelihoods of artists, writers, musicians, and other creative individuals. Ethical responsibility for the content generated by AI is crucial. If an AI produces harmful or offensive material, determining who is accountable becomes a pressing concern. Ensuring that AI adheres to ethical standards and societal norms is essential to prevent misuse and protect public interest. Addressing the complexities introduced by AI in creative domains requires the development of robust ethical frameworks. Organizations and governments are working to establish guidelines and policies aimed at promoting responsible AI use. Transparency and accountability are key components of these frameworks. Making AI processes understandable to users and implementing oversight mechanisms helps build trust and ensures that AI operates within acceptable ethical boundaries. Efforts to address bias and fairness in AI are also critical. By recognizing and mitigating algorithmic biases, we can prevent the perpetuation of stereotypes and discrimination, promoting diversity and inclusivity in AI-generated content. Considering the cultural and social impact of AI-generated content is necessary to ensure that AI contributes positively to society. This involves ongoing dialogue and adaptation of ethical guidelines to reflect evolving values and technological advancements. In conclusion, the Lovelace test represents a significant shift in evaluating machine intelligence, emphasizing creativity and originality over imitation. It challenges us to develop machines that can originate ideas rather than simply mimic human behavior. While current AI technologies may not fully meet the Lovelace test criteria independently, the potential for human-AI collaboration offers promising avenues for expanding creative possibilities and driving innovation. Recognizing the limitations of assessments like the Turing Test, there's a growing emphasis on incorporating aspects of consciousness, understanding, and intentionality into evaluations of machine intelligence. Ethical considerations are essential as we navigate issues of authorship, ownership, and accountability in the context of AI creativity. Looking forward, refining and developing new measures of intelligence will be crucial. Encouraging interdisciplinary research that combines insights from philosophy, cognitive science, and artificial intelligence will help us better understand and harness the capabilities of AI. By prioritizing ethical development and fostering collaboration between humans and machines, we can shape a future where AI enhances human creativity and contributes positively to society. Thank you for joining me in this exploration of machine intelligence and creativity. In the next chapter, we will continue to delve into the advancements and challenges in AI, examining how emerging technologies are reshaping our understanding of intelligence and the implications for the future. I look forward to continuing this journey with you.